Good morning and good afternoon, RSGA and viewers, and welcome to Newton's third law. For every action, there is an equal and opposite reaction. We're going to explore that in greater details here in a few moments. Now, to help with the context here, I hope you have watched the introduction, Newton's first law, and Newton's second law up to this point. Additionally, this information is provided on the basis it's for a 6th grade STEM class. And the information provided here is for that. If you want a deeper understanding of Newton's, there are probably other videos to watch for that, but this is what we got going on here. So there you go. Now, will those videos be applicable for 6th grade students? Maybe, maybe not. You know, we do what we can with what we got. So there you go. All right, so let's get into this with further details. Newton's third law tells us that forces always come in pairs. When you push against the wall, believe it or not, the wall pushes back on you with opposite force and of equal force. Why? Because you're not stronger than the wall is, all right? These forces act differently on different objects. One acts on the wall, one acts on you. In other words, forces always come in pairs. Okay, same thing with the ball on the table. I've used that analogy now 3 times. You put the ball on a table. If that table is flat, right, there's enough force being created by the table to suspend that ball. Okay, it's coming in pairs. In fact, it's going the opposite direction, right, than what is being applied. In other words, gravity wants to pull the ball down, but that table is keeping it suspended in equal strength. Okay, in fact, you could probably add something else to the table. It'll probably keep on holding it up until you add something that the table cannot withstand, right? Now, so that covers force comes in pairs, equal in magnitude in opposite directions. Additionally, they act on different objects. All right, right next to me, I have a wall. I'm going to push on it, right? As I push on it, I'm having to react with my feet and my lower section that I'm currently sitting with to kind of keep myself staying up. If I were to let my feet up, what's going to happen? I'm on a rolling chair. I have wheels. So I push, and sure enough, I move. All right? So other forces may change trajectories. Trajectory is where something is going. Remember that an object an object that is stationary wants to stay stationary. An object in motion wants to stay in motion, right? Right now I'm stationary. I am not moving, relatively speaking, right? But I apply a different force and I move, right? Now, I say I'm not moving, relatively speaking. That's because the Earth is moving. Would you agree with that? So technically, even though I'm still moving with the rotation of the Earth. And depending on which latitude you're at, that might be a different speed. All right, so let's take a look at the next slide here. Here's the big thing. A lot of students think that forces cancel each other out. That is not the case. Forces never cancel each other out. All right, they act differently on different objects. When you jump, you're pushing down on the Earth, and there's enough mass that, hey, when you're jumping, the Earth doesn't move, you move, okay? Because the mass of the Earth is greater than your mass, all right? So they're not canceling each other out. They act differently on different objects, all right? How far you jump is the amount of energy that you're exerting. Conservation of energy, right? Your muscles are conserving energy until such time as you're able to spring upwards, right? So think about it like that. So when that happens, okay, so like you're jumping, both forces occur simultaneously, right? It's not a cause and effect type of thing where they're canceling each other out. You happen and that happens. It's a law, right? I push against a wall and suddenly that wall is kind of pushing against me as well. I'm not knocking the wall over. Why? Because I don't have enough force to. That wall is strong enough to push against whatever force is working against it, all right? Equal forces don't mean equal motion. It really depends on the mass, as I just illustrated. I am not as dense or as strong as this wall is, all right? It would take superhero strength in order for me to go through this wall, okay? And this wall not to react to me like it currently does. But I don't possess that kind of level of strength, and chances are neither do you, and neither does that ping pong ball. So that raises a question. Mr. Cadle, what if we put like 1,000-pound ping pong ball on a table? What would happen? Well, chances are it'll probably fall through the table because the forces of gravity, the weight of the ball, is acting on the is the force of the gravity, right? The amount of mass on that, and it wants to pull towards the earth, right? Therefore, creating acceleration and changes, right? So it really does depend on the mass. All right, so think about what happens here, right? When you are walking, you are pushing on the ground, and the ground is resisting the change to move, all righty? So the ground pushes you effectively forward because you're moving forward with equal force. If I want to turn to this direction, which is my left, all right, I think on your screen it's your right, right? I'm going to move with my opposite foot to go in that direction. If I want to go that way, all right, I'm going to move with my opposite foot to go in that direction. Why? Because it's an opposite reaction, okay? When you're swimming, all right, you're pushing the water back behind you as the water is kind of resisting that change and helping you move forward. Rockets, they expel ignited gas downwards, and that gas pushes the rocket upward with thrust. Or think about catching an object. Anybody who's ever played catcher or played softball or played football? Alrighty, if you're going to catch the football specifically and you're catching it, that ball in its motion, in its weight, is going to want to pull back, and then you need to bring it down, right? If you're catching, that ball comes in and your glove moves a little bit around it, right? That's the recoil from the object, alrighty? It's that opposite reaction. But notice if the ball is moving forward, your mitt is in front of it, guess what? That is the opposite motion for decelerating the object itself. All right, if you're in my class, I'm going to go ahead and play this video, all right? Or I'm going to recommend that you play this video, and it is of Brittany Force as she rockets to the top in Gainesville. These vehicles are amazing, all right? And they really show acceleration, okay? You're going to see that this vehicle right here goes from stop and accelerates all the way to over 300 miles an hour in less than 1,000 feet. That is crazy. Now think about all the forces that are acting upon this, right? You have acceleration, which is what we're really pushing upon, right? You have the opposite reactions. You have tires that are spinning in one direction, which push the car in another direction. And it does it with such ferocity that those cars can achieve great things. Now, there's other technical things going on too, which we're not going to get into in the scope of this, but you kind of get the idea there. All right, so I'll play that for you if you're in the classroom, or you can play that in the presentation itself. If you're at home, look at Brittany Force Rockets to the Top in Gainesville, NHRA, and then you will be able to watch that video itself. Really cool stuff. Last thing I want to point out for right now is think about how things react. I'm going to do some experiments, I say experiments, some demonstrations here in the classroom. Why are they demonstrations and not experiments? Because we're not changing any variables, okay? We're not experimenting with anything. These are known things to occur. So we're going to watch what happens with a balloon, all right? I'm not going to spoil what's going to happen, but we're going to watch something with a balloon. We're going to watch something when an object lands in water, and we're going to pair that with a heavier object. We're going to do some pushing and pulling together. We're going to look at the object on the table, which I've already kind of described. We're going to look at invisible forces with the magnet and the paperclip, and of course, as I demonstrated, with the rolling chair. Alrighty, so don't miss my last video where we kind of summarize everything briefly and kind of put everything all together.